So yeah, as Hannah mentioned, we'll be talking about system-wide optimization. Particularly, this work focuses on California. And yeah, I work in the Energy Analysis and Environmental Impacts Division of Lawrence Berkeley Lab. So just a really high-level overview of what we're doing here. This model really builds off of three sort of different segments of work. So we have a really rich, spatially explicit biomass data set that some LBL colleagues, including primarily Hannah and others, have built up in past work. And then this gets paired with life cycle emissions analysis from different waste management pathways in California, again, done from LBL colleagues, mainly Corinne Scown and Sarah Nordahl and others. And we use those emissions impacts as inputs into this modeling work. And then the third component that this model builds off of is the techno-economic assessment of these waste management pathways. So what does it actually cost to build these facilities, to send waste around the state, things like that. So in this talk, in terms of the methodology, I'm going to be focusing a lot of what we're doing with the spatial aspects of the work in terms of how waste is transported and where it's coming from and where it's going, and then talking about the optimization model itself. So just for a little background, many of you may be familiar with the organic waste management space, but really the primary motivation for these efforts are to reduce short-lived climate pollutant emissions. So when organic waste goes to a landfill and it decomposes anaerobically, methane is released into the atmosphere. Even with landfill gas capture systems and things like that, there's still significant emissions. If this waste is diverted from the landfill and instead sent to, for example, a anaerobic digestion facility where that decomposition process is controlled and that methane can be harnessed, then we can generate renewable energy that is both dispatchable and can be used, for example, as a transportation fuel with existing technologies. Another potential benefit of keeping these wastes out of the landfills involves the nutrient recovery, which some of our ongoing work is focusing on, looking at, how can we take out really pure, high quality fertilizer streams to reuse those nutrients as well. So in California, we have this Senate Bill 1383, that's the short-lived climate pollutant bill, that has set a cap on the amount of organic waste that Californians can send to landfill. So there was a 2020 target, and then the main target starts in 2025, and it's set as 25% of a 2014 baseline. So there's a hard cap on the amount of waste that we want to allow ourselves to, organic waste that we want to allow ourselves to send to the landfill. And then based off of our past disposal patterns, we estimate that there's 12 to 14 million tons per year of new handling capacity that we will need in order to meet this goal. So that's already considering all the composting and other existing infrastructure we have in the state. And just based on sort of the way these facilities are built, this would mean anywhere from dozens to hundreds of new anaerobic digestion facilities needed. So we want to think about, with this really rapid growth of this infrastructure, can we be strategic about this? Where do we want to build these facilities? What technologies might we want to focus on? How can we utilize existing infrastructure? So for example, wastewater treatment plants that might have already built digesters with excess capacity, how do those come into play? And then there's a couple of different dry and wet anaerobic digestion types that are going to be in today's results. And then as this model gets built out, we have data and assumptions to expand to some other types. But this is very much ongoing work. So, we have some preliminary results today. Unfortunately, I don't have all the answers to all of our problems just yet. So we have our really rich biomass data set that I mentioned before, and we also seed the model with potential sites for where these facilities can be built. So as I mentioned, there's the existing wastewater treatment plant capacity, but then for new facilities, new digesters, we look at where in the state are waste handling operations already occurring. And the reason we limit potential new facilities to these sites is just based on where we've seen these facilities built already. They're typically co-located with either a landfill or a compost facility or maybe a transfer station. And just when you think about, neighborhood impacts, permitting, all of that, it can make a lot of sense to site these facilities together. So we have about 400 sites across the state that we put into the model as potential places for these facilities to be built. So getting into some of the methodology regarding our spatial data sets, we start out with, I mentioned 70,000 waste points, but in order to have a more tractable model, we looked at how we could cluster those waste points together in a way that was still as representative as possible to the spatial distribution of these wastes. So we performed a k-means clustering approach and set a criteria for how accurate we wanted our clusters to be. So this was, pretty subjective, but we said, okay, as long as 90% of the waste in terms of the tonnage of waste is within 10 kilometers of the, as accurate as we know location to be, then we'll be happy. And so we, for each waste type, so for municipal waste versus agricultural waste versus food processor waste, we run this clustering process and add more and more clusters until we reach that criteria. And so for a given number of clusters, you can look at the curve of how far off are you from your original location to your clustered location. So as you can see, if you, for this example data set, if you gave it 1,000 clusters, you end up with, 96, 97% of your waste is within 5 kilometers of its original point. And so this plot on the right is just a zoomed in plot on the left. So here we kind of put our criteria and then again, test out these different sizes. And so by doing that, we were able to reduce our waste feedstock data set down to less than 4,000 points. And this kind of, again, shows for, again, we did this for each waste type individually. So that's what all the colored lines are. And then the black line was kind of our overall statewide, how accurate this clustering was. So we had about 93 or 94% of the waste still within 10 kilometers of that original data point. Another thing we really wanted to focus on getting as right as possible was the transportation distance. So California is a very large state and very interesting topographically. We have the Sierra Mountains and then, another mountain range here. And if you've ever tried to do a road trip up the Pacific Coast Highway, you might get halfway and say, okay, I'm bored of all these twists and turns, and realize that there's no way to cut over to the main freeway. You would have to go all the way around these mountains. And so, that holds true for waste as well. Even if there's a facility that's maybe 10 miles from, or 30 miles from a given waste feedstock, that doesn't mean that it can just drive straight there. And so we wanted to make sure we were getting the transportation distances right, because one of the things we're trying to understand from this model is the trade-offs between a more centralized approach where you have a few extremely large facilities versus a more distributed, maybe even community scale approach where waste is staying more locally. So the way we handled this, initially we were doing this option where you are just looking at that bird's eye distance or the Euclidean distance and applying some blanket detour index. So some papers have estimated the national average is 1.4. And what that would mean is that the driving distance is 40% larger than that straight line distance. But again, California is very interesting and we wanted to be more accurate than that. So what we did is we ran 30,000 different origin and destination paths through a Google Maps, like a transportation API, so that we knew the true travel distance for those 30,000 routes. And then based on that, we can calculate this detour index on a very localized level so that in our model, for any given route, we can look at that set of 30,000 routes and find out which one was the closest and what that detour index was in order to be more representative. And so this just sort of shows here in the bottom right, we have all of the yellow points were the origins for the routes we assessed, and those are based off of our waste feedstock data. We kept reducing that data set down until we had 300 points. And then there's 100 destinations based off of the facility location data set to try to get good coverage of the state. So for the 30,000 routes we calculated, this shows the detour index of those routes. And this gray line here was that 1.4 national average estimate. And as you can see, you know, this line doesn't magically jump up to 100% at that point. There's a whole variation. So if you were to use that 1.4, you would always either be underestimating or overestimating the actual driving distance between 2 points. And then this shows some results for just a random sample of 15 of these blue destinations for all 300 origins to come to that destination. What were the different detour indices for that? And you can just see, you know, the wide variation. Some detour indices getting up to 3 or 4 and so on. But then variation in the averages as well. So, you know, more mountain or more remote locations might have a across the board higher range than others. And so just another similar view is looking at, this is just representing, so these yellow bars being the averages for a given destination. So remember, there's still going to be a lot of variation here, but just looking at the averages, we can look at the converse view, which is for each origin, what was the detour index to go to these 100 facilities. And on the left, you can see the full range of data points where there's one point, particularly in the mountains, where the average was around 1.8 detour index. And then on the right, I just shaved off a couple of that top 1%, those top few points, just so that you can get a better view of the variation across the rest of the state. So here in the Los Angeles and San Diego areas, as well as right in the San Francisco area, you, in a very urban place with a well built up transportation network. So you're going to have the opportunity to have a direct route to most places you want to go, versus again, up here in the mountains and along the coast, you might get a little more stuck and have to go around. And then just as like an interesting data point, the highest detour index in the data set was 6. And this is what it looks like, because, you know, a lot of these mountain roads just end. But it's good to have this data, because if you were saying we wanted to build a facility over here, you can't expect to take in waste from all of these mountain communities. It just might not make sense, or you would need to account for that transportation cost. And then the other, just last thing I'll mention with the spatial data is, as we run these models of diverting waste from landfills, we want to compare to the alternative of just sending that waste to the landfill as normal. So the sort of baseline scenario we're typically comparing against is the landfill option. And I had done some past work analyzing transportation of waste to landfills in California. And you can see that California organizes its waste data and its waste policy by these jurisdictions. And for each jurisdiction, there's both a wide variation in how far the waste, a given pair between that waste and the landfill. There's a wide variation in that distance, sometimes up to hundreds of miles, and even, you know, a lot of areas you see places putting waste onto trains and sending them even across state lines. So the transportation distance can also be very high for landfills, and it varies a lot depending on where you are in the state. So we account for that as well. Okay, and then just to mention kind of at a high level what we're doing with the economic modeling, the cost modeling. This is a very, very, very high level flow chart of what an AD facility might look like. So you have waste coming in to the digester, and then there's solid and liquid byproducts that we call digestate that need to be managed, and the transportation and disposal of those Typically, they need to either be sent to a composting facility or sent to a dedicated land application site, and that can be very expensive. And then, of course, you make your biogas, the mixture of methane and carbon dioxide. And there's two different pathways we assess in this model. One option is to combust that biogas on site and generate electricity that can be used on site, sold to the grid, maybe sold to a neighboring customer. And then, of course, you also do get heat back out of that. Some of that can be used by the digesters, but mostly we see heat being wasted from these CHP units. The other option for the biogas is to send it through an upgrading unit where you are removing the carbon dioxide or removing the methane, whichever way you want to look at it, to where you have a pure methane stream, and that's what can be used as a vehicle fuel in a compressed natural gas truck, for example, or it could be injected into the natural gas pipeline and then sent to any natural gas end use. So for these different facility configurations, both in terms of the energy pathway as well as what type of AD we're looking at, we model the mass and energy flows of where everything ends up, how much biogas is generated, and then costs and revenues at each of these points. And in this model specifically, we are really trying to focus on the sort of societal or economic costs. And so there's some differences here versus other modeling we've done in the past where we were looking more at an investor's perspective or private sector perspective. And then this just shows at a high level the facility cost assumption. So for wet and dry AD, so for all of these facilities, we assume an exponential curve to capture the economies of scale of these equipment. And there's some literature review that we did to get these costs as accurate as possible and then calibrated those curves to facilities that have already been built in California that we know the cost of. So for wet and dry AD facilities, we don't quite have enough information to confidently say that those costs are different. They kind of tend to all those data points exist in the same space. So we use the same cost curve for those. And then, as I mentioned, as we expand this model, we will be adding gasification facilities as well as dairy digesters. And then, but the third facility type that will be in the results today is co-digestion at wastewater treatment plants. So for that installation, it's much cheaper because we're assuming the digester is already built and already has that capacity to take in the waste. You just need to build handling equipment, so a storage tank and a blending tank and the associated pumps for that in order to take in extra waste and put it into the digesters. And then the last sort of methodological or input data set that feeds into this is the life cycle emissions estimate. So this was work that was done by Kernskown and others at Lawrence Berkeley Lab that has a recently accepted paper, should be published within the next few weeks on this. And so here they've looked at different scenarios of, this plot is just showing the results for dry anaerobic digestion facility, but we use data for other facility types as well. And looking at different configurations of, what you're doing with the energy. Are you sending electricity to the grid? Are you using it to fuel trucks? Looking at alternative baseline scenarios of landfilling and composting, and then calculating the per ton of waste, what the emissions impacts are. And so this plot shows for the greenhouse gas emissions, and we also have data for ammonia, PM, and other pollutants of interest. And so in this optimization model, we use these results. We say to take 1 ton of a given type of waste and send it through a given type of facility, what are the emissions impacts of that? And then separately, we have emissions factors for transporting that waste, and so that the model can more dynamically say, okay, we're going to send 1 ton of waste through this facility, and then we want to add how much emissions there are from transporting that waste, and then we also consider the baseline of, you know, where that waste would be going if it wasn't going to this facility. So when we put all this together, we build up an optimization model that I'll move pretty quickly through the actual formulation of it, but I have all the information here if there are questions. But at a high level, we are doing a mixed integer linear program, and we're doing a multi-criteria optimization because we really want to consider both the emissions benefits of this infrastructure system as well as the cost. And so we construct a Pareto curve, which is sort of the frontier of, you know, any trade-off between emissions and cost, what's the best you can do. And so in order to construct this curve for any one given scenario, we need to run 8 to 10 model optimization runs. So to get these two endpoints, I'll just kind of walk through a brief example. First, you run the model just to minimize costs. You say, I don't care about emissions. All I want to do is the cheapest thing possible. And so you might get a point somewhere up here that has a really low cost and high emissions. And then second, we then say, okay, I want to keep that low cost, you know, maybe add a buffer of 1% or 2% of the total cost, but then I want to minimize emissions. So that's the second model run, and that gets you this one endpoint of sort of what's the best you can do in terms of cost, but then also consider, you know, at that cost, what's the best you can do in terms of emissions. And then 2 more model runs on the converse of that get you the endpoint for the lowest emissions. And then for every midpoint, we constrain, in this case, we're constraining the emissions at intermediate levels between these two extremes. And for each, you know, constrained emission, we minimize the cost. So that makes sense. So yeah, so that's kind of the framework we're working in terms of the multi-criteria optimization, and there's a lot of modeling that has to take place to get, you know, a good set of results. So just a little more about the model at a high level. We can also add in constraints for a couple of policy scenarios that we want to analyze. So looking at, just check my time. Okay. Looking at diversion mandates or energy generation mandates and say, okay, if, you know, if we force the system to make a certain amount of bioenergy, is that something we actually want to be doing, or maybe it's causing us to spend more money and not get benefits or something like that. So we can build in extra constraints, and then we consider the capital and operating costs of the facilities, the market value for the energy products. Again, we're looking at a societal cost perspective, so things like carbon credits or any sort of policy incentives that aren't considered an economic cost, but actually a societal, like, economic transfer. We don't consider those in this model. We just want to say, you know, what do we actually want to minimize costs and emissions? And then, as I mentioned, we consider the baseline scenario. So any municipal waste or food processing waste, for now, our baseline assumption is that it's going into the landfill. And then for like agricultural residues and some things, we assume that those are just left to decompose on field. And as we run more scenarios, we'll be playing around with different baselines in terms of composting, burning of residues, and things like that. I don't want to really spend time on the formulation, but again, this will be in the slides for anyone who's really interested. Here's our 2 objective functions. So again, we have emissions and costs, and we can tell the model, you know, which one we want to use and which one we want to constrain for a given run. Basic constraints. Okay, and so some of the preliminary results I want to show today are based on doing regional modeling in California. To run, you know, even with the condensed data set in terms of waste points and facility locations, just running one of these regions has anywhere from 1 million to like 2, 3, or 4 million decision variables in the model. So computationally, it can become very large and take a very long time. And we are utilizing some high performance computing resources at Lawrence Berkeley Lab but it's still, we're still trying to scale up to really doing that full statewide model in a timely manner. But today I have some results for some of these regions. So just to give you a brief overview, this is what I'm calling the Bay Coast region. So San Francisco is right here, and all of these blue points are the wastewater treatment plants that have capacity available in the model. And the circles are different waste points in the model, and the X's are potential facility locations. And then this is the northern part of the state. So you can see this map sort of nestles in right here. This is a much more sparsely populated area, but it does contain the northern Central Valley, which is a pretty rich agricultural region. So you have a lot of these agricultural coals and residues available here, but there's a lot less people, so a lot less wastewater treatment plants and municipal solid waste. So this was kind of whenever I was initially doing this presentation a couple weeks ago, this was sort of where we were at in terms of getting some of these model runs done. We hadn't quite constructed a full Pareto curve, but we were able to run 5 or 6 scenarios for each region and get a few data points. So this is kind of where we're heading. I don't want to focus too much on these absolute values because it's pretty preliminary, but yeah, we'll expect to see, as we start running more of these midpoints, we'll expect to see sort of this curve where at a very low cost, you might have a steeper slope here, which represents a lower abatement cost. So I don't have to spend as much money to get more emissions reductions versus way out here, my emissions are already very low. It might be very, very expensive for me to get that next marginal unit of emissions. So once we have these Pareto curves, one of the things we can look at is the abatement costs for different systems and kind of where, if we want to assign, for example, social cost of carbon, where on that curve might we want to land in terms of these trade-offs, and then what does that system look like? And this just kind of walks through some of the results for the scenario. I only have a couple more minutes, so I'll just show, this is for minimizing the cost. You can see in the northern region, there was a couple of dry AD facilities built that took in food processing waste, so that's this yellow bar here in the north, and municipal solid waste, so that's food waste as well as like yard waste, things like that. And a couple of, in red, these larger red circles are the wastewater treatment plants that were utilized in this model run. So even with only focusing on cost, we are still seeing a significant amount of diversion because the baseline scenario is sending this waste to landfill, and that there's a tipping fee and there's a societal cost associated with that because we're using that landfill capacity. So what this is showing is that, at least for our preliminary results, even if all we care about is money, there's significant amount of diversion that we want to be doing, particularly when it comes to these waste streams that are currently going to landfill. And then I'm just going to skip to, this is the same set of results, but for the minimum emissions scenario. So this is both at the minimum emissions, but then also minimizing the cost. So this is that endpoint of the Pareto curve. And we see if we want to minimize emissions, we want to process basically as much as possible, because anything we send to an AD facility, we are generating renewable energy and reducing landfill emissions, or in the case of municipal waste, we're reducing landfill emissions. So here we see a lot of wastewater treatment plants being utilized. These larger circles represent like the big wastewater treatment plant in Oakland and San Jose. Those are being used to their full capacity. And then we see mostly dry anaerobic digestion facilities being built, and that's primarily because these facilities can handle both wet waste like food waste as well as drier waste like yard waste and drier agricultural residues. And so if you build dry AD facilities, you can build them larger and capture more of those economies of scale while still taking in all of the waste in the region. And then this just sort of shows for the wastewater treatment plants in the 2 regions how much of that excess capacity the model chose to utilize. So Yeah. So yeah, as I mentioned, this work is very much in progress. The next step is, of course, getting the full set of results done. And then we're going to be playing around with some sensitivity analysis, both for our emissions assumptions as well as costs and mass balances and things. And then looking at some different baseline scenarios and some new facility types to help us understand the role of composting. Because in all of these landfill diversion policies, composting is, a valid diversion pathway, but when it comes to municipal waste and food waste, there's a lot of limitations to traditional outdoor composting, and there's limitations to what facilities exist to handle those wastes and are willing to handle those wastes. So we want to see, based on what we know about how these facilities operate, how much can we really depend on composting facilities and how much are we going to need this more advanced infrastructure. And then running the model at different geographic scales, so maybe for an individual county and then for the entire state, can give us an idea of what benefits we might be able to gain from doing more regional or even statewide coordination of this infrastructure build out. And then, of course, ultimately, we do want to look at different policies and how they're impacting the system, the mandates I mentioned, as well as upstream policies that aim to reduce waste even being generated to begin with. We can see how, maybe in the future, if we are wasting a lot less food, maybe we won't need these hundreds of facilities to handle it. So kind of how does the upstream reduction save us money downstream, save us emissions, and maybe we want to make decisions based on what we think the future waste stream will look like. Okay, so I think I'm just 1 or 2 minutes over. Thank you all, and I'm happy to take questions at the end of the session, I think.
Wonderful. Well, actually, just to give you one chance, we can take the one question that was typed in, and then we'll move on to Katerina. So let's see, there was one question about the end. If you can see it, I'll record them, but there was a question earlier on about what the true cost is beyond just economic cost, social, environmental, and how complex is it to integrate those two. So why don't we do that question?
Yeah, so as I mentioned, in this model, we're doing the optimization of both the costs, the economic costs, as well as the emissions. And in this case, we're focusing on the greenhouse gas emissions, but as our upcoming publication will show, another thing that's really important in terms of total societal cost is the human health impacts of some of these waste operations. So particularly with composting of food waste and of digestate, there are concerns around ammonia emissions and yeah, primarily ammonia. When you run our life cycle emissions results through some of the reduced form air quality models that show societal cost of different pollutants, ammonia becomes the most expensive because it can be damaging to health. And so the way we're addressing that right now is we're optimizing greenhouse gas emissions with costs, but then for the resulting scenarios, we'll be estimating the emissions of those other pollutants and looking at the costs, and then maybe later on we could assign those social cost factors into the model and do like a completely aggregated societal cost optimization as well.